Hi, Assalamualaikum and a very good morning. We are still in chapter 1, which is reaction kinetic, but we are on subtopic of 1.1 reaction rate, part 3. So if you haven't watched part 1, please watch it now. In this video, we're going to learn what is meant by the integrated rate equation for zero, first and second order reaction. We're also going to look into the definition of half-life, which is T1/2. And then we're also going to determine the order of the reaction based on the half-life where it is gotten from the graph of concentration against time, and also looking at the linear graph method based on the integrated rate equation and also rate law. Last but not least, it will also be supported with the calculation using the integrated rate equations that we will going to look into in the earlier part. This will also be supported during the tutorial session. Alright, without any further ado, let us start. Okay, for a zero order reaction, it is basically a reaction independent of the reactant concentration. So if we were to consider the reaction of A going into the product, we can say that the rate law is equal to rate is equal to Ka to the power of 0, where A to the power of 0 is basically equal to 1. So rate is equal to K. So if you were to plot a reaction of rates against concentration of A, we will get a straight line parallel to the x-axis. Alright, so K gonna equal rate gonna equal to K. Now, in order for us to get into the integrated rate law for the zero order reaction, we have to derive the equation from the rate law. Okay, so it will be started up with rate is equal to K, because you know that A0 is equal to 1. So rate is basically the change in the concentration of reactant A over time, right? So you will bring the dt term on the right hand side. Okay, so you will get dA equal to K dt. Once you do that, you're gonna integrate both sides from 0 to a certain time t, and the concentration will start from A initial, which is A0, until A at time t. Alright, so once you do the integration, you will get negative A minus A0 equal to Kt. So as you do the maths and make the negative into the brackets, you will get A0 minus A equal to Kt. So lastly, you will get the integrated rate law for the zero order reaction going to be A0 minus A is equal to Kt. So you can just only use this for your for at least for matriculation level. The derivation here is not required. Okay, but I'm just showing you here so that you can understand where the integrated rate law is coming from. So you know that it is coming from the rate law, and we can use integration in order to get the integrated rate law. Alright. Okay, from the integrated rate law, you can draw the graph of A0 minus A equal to Kt. As what you can see here, it seems like a linear relationship where this one refer to y, here refer to m, which is the gradient or the slope, and t here refer to the x-axis, which is ymx plus c. So y gonna be the A0 minus A gonna be at the y-axis, t gonna be at the x-axis, and the gradient here, which is representing a slope k. You can also bring this term to the right hand side and Kt to the left hand side, and you will get A is equal to negative Kt plus A0, where we're going to construct A as the y-axis, mx plus c. So m, our gradient here, going to be a negative k, and the x-axis going to be time, and the intercept going to be A0. So this is the usual way of how we write the how we draw the graph. And also from the integrated rate law that we have derived just now, we can make a half-life equation. So we know that at halftime, the concentration of reactant at that time going to be half of the initial value. So A is equal to A naught divided by 2 because of the halftime. So if we were to plug in the value where we were substituting the T equal to T half and A equal to A naught over 2, we will get A naught minus A naught over 2 is equal to KT half. So once we do the math, we got A naught over 2 is equal to KT half. So we need to make T half here as the subject. So at last, we will get T half is equal to A naught over 2K. So this is what we needed at least for our level here. Alright. So just now we have looked into the integrated rate law and also the half-life of the zero order reaction. Now we're going to look into the example. So the decomposition of ammonia on tungsten at 1100 degrees Celsius is a zero order reaction with a rate constant of 2.5 times 10 to the power of negative 4 molar per minute. Okay, so the reaction equation is given as here. NH3 going to N2 plus hydrogen gas. So first we have to write the rate equation for this reaction. So the rate equation is the same thing as the rate law as what we have studied in part 2. So rate is equal to K NH3 to the power of 0 because 0 is a zero order reaction. It is not equal to the NH3 to the power of 1 because rate law does not depend on the stoichiometry. So this one is wrong. And as you will know as well, NH3 to the power of 0, whatever the concentration to the power of 0 will equal to 1. So we can just say that rate is equal to K. So next, we need to find the half-life of the reaction when ammonia is 0.75 molar. So we have looked into the half-life of the reaction in the previous slide, where the formula going to be T half is equal to A naught over 2K. So the ammonia concentration is known, which is 0.75, and 2K, where K is given, which is 2.5 times 10 to the power of negative 4. So once we do the math and cancel the unit, what we left is minute. So we'll get 1500 minute. Next, for part C, it tells us how fast is a 0.475 molar of ammonia being changed to nitrogen and hydrogen. Okay, so it was telling us what happened if 0.75 is reduced to 0.475. Okay, so basically the rate will still be the same because it does not depend on the concentration of the ammonia. So rate is still equal to K, where K is equal to 2.5 times 10 to the power of negative 4 molar per minute. And this is because zero order reaction is independent on the reactant concentration. Now we're going to look into the integrated rate law for the first order reaction. Just now we have looked about the zero order. Now we're going to focus on the first order reaction. So basically, first order reaction is a reaction whereby its rate depends on the concentration reactant raised to the first power. Okay, so the rate law going to be K equal to A to the power of 1. And this is what is meant by the first power. So if we were to plot a graph of rate against concentration, we will get a straight line graph representing K as its gradient. Right? And the plot of the reaction rate will passing through the origin. So the rate law can be used in order to find the integrated rate law, where we will use the derivations once again. So, but I'm not going to show it here. You can ask your tutorial lecturers to help that with the derivation if you are interested. And at the end of the derivation, you will get ln A is equal to negative KT plus ln A naught. So you can use this equation straight away, which is ln A is equal to negative KT plus ln A naught. Alright, so you can just focus on here, at least for this level. Alright, so once you know this integrated rate law, you can basically construct a line graph where ln A gonna be the y-axis, and here gonna be the gradient t gonna be the x-axis, and ln a gonna be the intercept. All right, and k here refers to the gradient, or this can be rearranged into ln a or ln a naught over a is equal to kt. All right, so you can bring this term to the left hand side and that term to the right hand side, and ln a naught minus ln a is equal to kt. So you will get ln a naught over a equal to kt. So you can also use that as the basis of your graph. But usually we will be using the one in the left hand side here. Okay, and we also can do this from the integrated rate law. We can also find the half-life by using the same technique as I shown in the zero order reaction, where we know that at t half the concentration of A gonna be reduced by half from the initial concentration. So if you were to substitute t half into here and A naught, A equal to N naught over 2 into here, we will get something like this. So here and here can be cancelled out, and 2 gonna be the subject. So it's gonna be ln 2 equal to kt half. So the half-life t half gonna be ln 2 equal to k. So you can use this as your half-life for the first order reaction. Alright, now let's look at the example. So for the first order decomposition, first order decomposition of hydrogen peroxide, given that K is equal to 366 times 10 to the power of negative 3 second per minute, a second per second, and the initial concentration of hydrogen peroxide is 0.882 molar. Determine the time at which H2O2 is equal to 0.6 molar. So we can use the integrated rate law, where ln is equal to A naught over A. But A here we refers to the hydrogen peroxide, H2O2. So the initial concentration is known, and the concentration of H2O2 can be calculated here, which is 0.6, and then K is also given, and we need to find the time. So we got ln 1.47, and we were going to divide it by the value here, so you will get 105.26 seconds. Now we're going to find the concentration of H2O2 after 225 seconds. Okay, so we can use the same technique where we know the initial concentration, which is 0.882, but we now need to find the new concentration after 225 seconds, and the rate constant can be plugged in here. So you need to be very careful with this. So do it one side to one side first, where you settle this one, and then you will bring the log, the natural log, to the right hand side here, and then only you do the cross multiplication. So the concentration of H2O2 you're gonna get is 0.387 molar. Alright, so both of these example here use the integrated rate law for the first order reaction. Now we're going to look into the second example for the first order reaction as well, where the ethane C2H6 decomposes to form methyl radical with a rate constant of 5.36 times 10 to the power of negative 4 per second. So it asks us to calculate the half-life of the reaction in minutes. So what we're going to do is to use the half-life, where we have derived this just now, where it's equal to ln 2 over k. So ln 2 is, as you plug in the calculator, you get 0.693. K is given here, 5.36 times 10 to the power of negative 4 per second. So you will get 1.29 times 10 to the power of 3. But remember, they asked us to find it in minutes, here in second. So second convert to minutes, you will need to divide by 60. So you will get 21.5 minutes. Alright. Okay, now we're going to look into the integrated rate law for the second order reaction. So the rate law for the second order reaction going to be rate is equal to Ka to the power of 2. So the integrated rate law that will be gotten once we derive the equation and integrate it. So we're going to get 1 over A equal to 1 over A naught plus Kt. Alright, but as I mentioned, the derivation is not required yet. At least for your level, you can directly take the value for the integrated rate law for the second order. Okay, and now you can find the relationship of the graph of rate with concentration. So for the second order, you will be getting something like this if you were to draw rate against concentration. But if you were to draw rate against the concentration square, you will get a straight line graph because it's going to be y is equal to mx. So your x-axis is going to be a square, and the gradient that you will be getting is equal to k. Alright? And based on our integrated rate law, we got 1 over a is equal to 1 over a naught plus kt. So the same as before, it is a linear relationship where you got y is equal to mx plus c. Okay, so 1 over a is our y-axis, our x-axis is going to be t, and our gradient going to be k, and our intercept going to be 1 over a naught. Alternatively, you can bring 1 over a naught to the left hand side and also create this kind of graph based on y equal to mx. However, we often use this one because it gives us the intercepts. Alright. For the half-life, it's basically the same technique as I shown in the first order and the zero order reaction. So based on the integrated rate law, you basically plug in the value of t is equal to t half, where the concentration of A gonna reduce by half from the initial concentration. So A is equal to 1 over A naught over 2 is equal to 1 over A naught plus Kt half. So it's equal to 2 divided by A naught equal to 1 over A naught plus Kt half. So you can bring this term to the left hand side and you got Kt half. So the last that you will get is T half is equal to 1 over Ka naught. So this is the half-life of the second order reaction. Okay, so this one is important and this one is also important. Now we're going to do some example regarding about the integrated rate law and half-life that we have studied for the second order reaction. So it says here that iodine atom combine to form molecular iodine in the gaseous phase. Okay, so this reaction follows a second order and has a high rate constant of 7 times 10 to the power of 9 per molar per second. If the initial concentration of iodine is 0.086 molar, so you know that the initial concentration of iodine going to be 0.086 molar. They ask us to calculate the concentration after 2 minutes. So we can use the integrated rate law here. And we need to find the concentration of this one, the A here. So A naught is given, which is 0.086, which is the initial. K here is 7 times 10 to the power of 9. And T here, you really need to be careful because the rate constant is given in second. Okay, but it says after 2 minutes. So 2 minutes, basically you have to convert into second first, where 2 times 60 equal to 120 seconds. Alright, so once you do that, you will get 8.4 times 10 to the power 11, and you invert that, you will get 1.19 times 10 to the power of negative 12 molar. Alright, and for the second question, you have to find the half-life of the reaction if the initial concentration of iodine is 0.06. So you can use the formula straight away, where T half is equal to 1 over Ka naught, 1 over substitute the value. K is given and A naught is also given. And lastly, you will get 2.4 times 10 to the power of negative 10 second. Alright. I think this one is quite direct. And on the last page here, I've made a summary regarding part 2 and part 3 for the zero order, first order, and second order reaction. So you can see here the rate law is different from one another, and the unit for the rate constant for each order is also different. I also given the half-life and also the integrated rate law as well as the example of the graph here. So you can use this as the basis of your study, which I find it very, very useful, so that it can help you in your learning. Okay, I think that's all for today's video. See you again some other time. Bye.